Welcome, welcome, welcome to Minerals, Rocks, and Fossil Talks. I'm Matthew, and
I'm Jennifer.
And today we're going to be talking about the inside of the Earth.
So, as most of you are aware, the Earth is a giant ball, but it is not a hollow ball, it is a solid ball with lots of layers.
Yes, there are in fact 4 layers, kind of. Depends on how you count them.
4 major layers. Those are the important ones. We won't worry about it unless you really want to ask us in-depth questions later.
Exactly. But the first thing to notice is the crust. Look down at your feet.
Frosting on the cake.
Yes. Look down at your feet for a minute. The stuff you see beneath your feet, assuming you are outside, that is the crust. If you're not outside, look out the window. That's the crust. Unless you're on a boat, in which case the crust is anywhere from several dozen feet to a couple of miles below your feet. But let's not labor on that point.
And much like the crust on your bread, it is very thin.
Yes.
Compared to the rest of your.
Now the crust can range from just from a few dozen feet to several thousand, depending on where you are. Obviously, it's thickest under the mountains. I believe the thickest point of the crust would probably be in the Himalayas.
Yes, it would be. In fact, it is so thick and heavy that it's actually sinking into the mantle, which is the layer below it. So while it is still, separate, it's still the crust. It's so heavy that the highest point is actually sinking.
And it's thinnest at under the ocean. That is where new crust is born, which actually leads us very nicely into the mantle.
Yes, so the mantle is this nice big green section. And I actually did that on purpose because the majority of the mantle is made out of a rock called peridotite, which is a green mineral.
Yes. Now the mantle is, the upper portion is mostly solid. The inner portion is more liquidy. Now it's still very, very hot. Hot enough that when you see lava erupt out of volcanoes, that's actually coming directly from the mantle, essentially.
Think of the mantle as the consistency of hot wax. So it's still solid, but it's hot enough and fluid enough that it can move and flow.
Exactly. Pour out a melted candle sometime, or don't. It's probably a bad idea. But that will give you an idea of the consistency of the mantle.
Or molasses.
Molasses is also good and also messy. So I would also not suggest that.
But you can eat that if it makes a mess. So
exactly.
I'd recommend doing that over the wax.
But yes, that's where lava comes from. When you see lava spewing out of volcanoes as 2 Jedi Knights fight on the planet Mustafar, that is coming directly from the mantle. I put a Star Wars reference in the first one. I'm going to try and sneak one in every episode.
That's fair. I'll probably end up doing Harry Potter at some point.
It makes sense.
To add on to that, so the part of the crust where, in the oceans where it's making the new crust, most of that crust is basalt and gabbro, which is the stuff that's coming out of the mantle. So it's the same stuff, it's just now on the surface. And now that it's on the surface, it's weathering. So it's gonna be slightly different because of the chemical changes from the water and the salts and all the other fun things that are happening in there that we can talk about later. But know that it is technically the same stuff.
Additionally, lava is not always exactly the same composition. When you see really explosive eruptions, as in if you watch eruptions of Mount St. Helens, you get that's the thicker kind of lava that gums up at the top of the volcano and eventually pressure builds, leading to those kinds of gigantic and really, really cool explosions.
A lot of it also, and we can get into more detail on this when we talk about igneous rocks, but another thing, just to keep it simple, is that the composition of those lavas also depends on what depth in the mantle it came out of as well. So the difference in temperature and pressure from these layers of the mantle will actually change the composition.
The more flowy kind is actually still really, really slow moving. You can outrun a lava flow in Hawaii. Not that I'd suggest you try it, but you can. It goes probably 3 miles an hour at the very fastest. That kind of lava oozes out very nicely and slowly, not gumming up and therefore not getting that pressure built up to cause explosions. And therefore you can see those rivers of lava coming down.
Probably also helps with gases being bubbled up either.
Yes, that as well.
See, even the Earth has gas problems, guys.
Yes. Now, moving on to the core. The outer core is mostly liquid. It's this red part, red for hot. The outer core is the hottest part, but that's pretty much all liquid iron, and that's what causes Earth's magnetic field, which helps us not only with dating fossils and rock layers sometimes, but can also help with...
it makes your compass work so you don't get lost when you go out hiking by yourself because you didn't take your buddy.
It makes it so your...
all the navigation equipment.
Yeah. It also, the magnetic field helps create the auroras as it reflects solar wind around Earth during sunstorms. I know we're talking about space and this is a geology channel, but trust me, everything is connected. I know all scientists say this, but geology is really the key to understanding the world more than just about anything else. I know chemists will say that and mathematicians will say that, but that's at a much more meta level. You can actually see geology working. You can't usually see the chemistry unless you really know what you're talking about.
Take it from our experience, we literally had to take at least 1 to 2 of all the science courses. The other sciences don't have to do that.
That is true.
We needed a little bit of everything, so I think that shows us just how important geology is.
So these, the outer core helps with all of that. Now, how do we know that we have a liquid outer core?
Earthquakes! Sorry,
yes.
I love them.
But you can measure how quickly an earthquake travels through different materials. And just like if you take 2 things underwater with you, you take 2 rocks into your pool and click them together, the sound travels much further through water because water is thicker than air. Now you can't go underground the same way you can go underwater, but those same waves will travel more quickly through cement than it will through water. So, by measuring the effects of an earthquake on the other side of the world from where an earthquake happens, so say you are in San Francisco and an earthquake happens in Japan, you can sense on seismographs in San Francisco where the exactly how the earthquake reflects from the epicenter in Japan to your station in San Francisco. And because we know how fast these waves travel, you can tell how quickly it managed to get there, and it slows down in the outer core. Therefore, outer core is liquid.
Which moves us on to the last bit of our Earth, which is this chocolatey goodness, the inner core, which is a solid iron-nickel alloy. And this little core here is what's keeping the Earth together. it's created our gravitational pull so that we stay in one spot in one nice little ball.
Another fun thing about the inner core is it's actually the heaviest part of the Earth.
Which is why the gravitational pull originates
Yes.
from there.
Even though it's smaller geographically than the mantle or the outer core, it's much heavier because it's solid and therefore more dense. And finally, there are a couple of what I might call sublayers in there. So, for instance, you'll hear geologists talk about what's called the lithosphere a lot.
So the lithosphere is the crust and the uppermost part of the mantle. So that's where all of our plates sit. That is where the plates are, and it's basically just that little chunk. So it's not really very thick. If I were to like arbitrarily draw a line, it's really just very, very thin there.
But when you'll look at diagrams in geology books, and you'll see, for instance, you have the North America plate here. So my fingertips are California, and then my other hand is the Pacific Ocean, and the Pacific Ocean is diving very shallowly under North America. That part that the Pacific plate is diving under the North American plate into, that's still part of the lithosphere.
However, the section below the lithosphere, the asthenosphere, is what's causing the movement to begin with. So the asthenosphere is the part of the mantle that flows, and it's the things that's making our crust wiggle.
So when you hear about continental drift, which I guess that's an old-fashioned term, but people still use it sometimes.
We'll talk about it in the next episode.
But the subscribe. But the asthenosphere, or the continents flow over this liquidy part of the mantle, is what's driving Africa north, North America west, little parts of California, Oregon, northern Mexico north, Australia north. I guess most continents are moving north, huh?
Yeah.
But that little section of East Africa causing it to flow away from the main part of Africa, maybe, is complicated. But,
well, there's this sort of half-dead rift in the middle of our continent, too.
oh, yeah, that's
The
true.
Rio Grande Rift that goes through Colorado, New Mexico, and part of Mexico.
Yeah, so eventually that might also split off, and we don't really know what's going to happen there. All of that is flowing because the upper mantle, this part, is convection. There's convection of the heat going on in there, and that makes the mantle move, and that makes...
I'm gonna say something. They couldn't see what you just did because there's a dinosaur in the way.
Oh!
Whoop.
This part of the mantle here is what makes the upper part of the mantle and the crust move, and making Australia, Africa, South America is mostly going west also. But South America is kind of going north. North America to the west.
So a fun thing, because you'd mentioned convection, I've actually done some reading, and they're not so sure if they're holding to the convection thing.
Really?
Yeah. I don't know
I
what
did not
they're leaning toward, but they're like, I don't know if convection's really what's happening. But that's science for you.
Yeah.
Learning new things all the time. So if we find out anything more in the future, we'll let you know.
Yes. But yeah, geology is, even though it moves very, very slowly, we update our knowledge very, very quickly. So even just a couple hundred years ago, nobody thought that the continents moved at all. That's...
And now we're
relatively
using
recent.
what we know about our Earth to figure out other planets like Mars, where because it doesn't have these processes anymore, like the inside of the planet's essentially dead, and that's why there's nothing alive. There's no water left. They found traces of these things. It used to be there, but the surface stopped moving.
Yeah, And presumably they've found other planets that are roughly Earth size and in what's called the Goldilocks zone, where it's warm enough that liquid water is going to be there, but not so warm that life is going to get the crap baked out of it. Presumably, similar processes will be working in those planets as well, with the energy from our sun, their whatever star, I don't know what star they orbit, but helping create energy, create life.
Yeah. So that is the Earth in a cake, because it's not a nutshell.
Yeah. But just remember, frosting is the crust, green portion the mantle, red portion the outer core, chocolate portion the inner core. And there you go. That's how it works. That's the Earth.
So now that
Very
you know
briefly.
about the inside of the Earth, you can go tell your friends how much you know now. And make sure that you like, subscribe, and hit the little bell for notifications so that you can keep up to date with us. And when we're not posting videos, you can go to our Instagram and Facebook page where we post daily fun facts to keep you interested in between them. So next episode, we'll start talking about fun things like seafloor spreading and continental drift and plate tectonics.
Earthquakes, volcanoes, Pangea. Yeah, that might be.
Not yet. Just the history part of it, really.
Right, yes.
But it'll be fun.
But continental drift, Pangea, seafloor spreading. We'll probably talk more about that half-dead rift in Africa.
I don't know how to end these yet, but...
Yeah, me neither. Good talking to you guys. We will be back. More cool geology information with you. Toodles. I'm losing my train of thought. I should have scripted this, but you can cut this out. Then